So in this tutorial, I will take you on a journey through the universe of noise, unraveling the mysteries behind white, pink, brown, and blue noise. But we won't stop at just theories and definitions. We'll go hand-on with Python, using its powerful libraries and visualization capabilities to bring these concepts to life. Noise, often seen as an unwelcome companion in our signals, is far more than just random fluctuations. It carries patterns, characteristics, and even unique behaviors that we can harness and manipulate to our advantage. Whether you are studying communication systems, analyzing data, or developing cutting-edge technologies, a deep grasp of knowledge can give you a competitive edge. So why would you dive into this tutorial? First, understanding noise empowers you to create robust and resilient systems that can thrive even in the presence of disturbances and randomness. Second, it broadens your perspective by connecting theoretical concepts to practical applications, making you a well-rounded engineer or a STEM student. Lastly, the knowledge you gain here serves as a stepping stone for delving into advanced topics like filtering, data analysis, machine learning, artificial intelligence, and advanced signal processing. So are you ready to revel the fascinating world of noise using Python as a guide? Let's get started. So firstly, we have to understand where does noise get its colors from. For that, we turn to visible light. And as seen on the slide, you can see that when we go from bottom to top, the frequency is decreasing. So red is the lowest frequency of the visible light. And as we keep going down, we reach to violet color. Now, why are we talking about frequencies? It so happens that noise exhibits a very special characteristics, which is often known as 1 by F. The power spectral density of noise is dependent on the frequency of noise. And without getting into deep mathematical understanding and derivations of this formula, let's just take it on face value that the power spectral density of noise is closely related to its spectrum and defined by a formula called 1 by F raised to the power beta. We will see more about it in the next slide. So depending on what the value of this beta is, the color of the noise gets decided. So if beta is 0, for example, this F term turns to 1 and the power spectral density becomes 1. And this is what is the definition of white noise. If we keep coming down, if this beta becomes 1, then we are this expression becomes 1 by F. And that's the classic definition of pink noise. If this beta becomes 2, it has a very special term for it. It's called Brownian noise or brown noise, also known as random walk. It's a very important concept in almost every engineering field, including econometrics and finance. On the other side, if we assume the value of beta to be -1, then the noise is known as blue noise. So 1 divided by F raised to the power -1 is nothing, but the power spectral density is now proportional to the frequency. This F goes on top. And if this beta becomes -2, then the color of the noise is purple. We are going towards high frequencies. And essentially, the power spectral density is proportional to square of the frequency. So without getting into too much of mathematics and how this formula has been derived and why beta is supposed to have these kind of values, let's generate these noises using Python and see what they mean. Starting from the white noise. Now, white noise is nothing, but it is a Gaussian distributed noise, or it's a noise which is following a normal probability distribution. And this is the formula of Gaussian probability distribution, where mu is the mean and sigma is the standard deviation of the noise. And in time series, it looks something like this. So if we say mu is 0, that means the noise is going to be centered around 0 axis. And this sigma decides the fluctuation of this noise around the mean, that is these amplitudes. If this sigma is a low value, these amplitudes will be fluctuating in a very narrow band. And otherwise, if the sigma is a large number, then this signal will have very wild amplitude fluctuations. And that's how this white noise gets generated. So let's switch over to Python and try to generate this noise. So here we are in Python environment. I have imported some Python libraries to make this code run. So initially, we will investigate this formula, the power spectral density formula, which is 1 by F raised to the power beta, and see how this function behaves with changing powers of beta. So I have divided this beta into two parts. The negative part is having the value -2 and -1, and the positive beta is 0, 1, 2. And I have created a frequency axis which is going from 1 Hertz to 3 Hertz and is having 1000 numbers in between. And also for the purpose of giving colors to this noise, I have used some palette here for the negative beta and for the positive beta. And the most important part is that essentially I'm implementing this formula. I have F here, which is frequency, and this beta is being extracted from this list, these lists, negative beta and positive beta, from in this for loop. And then we are going to generate this plot. So this particular loop is for negative betas, and then there's a second loop which is generating plots for the positive beta, implementing the same formula. So let's run this code. So we have some very interesting plots here. Our x-axis is f-axis representing frequency, and our y-axis is the power spectrum. Essentially, at the cost of repetition, I'll just once again repeat that we are trying to investigate power spectral density formula of noise. And what we see here is that when the beta is -1, then this blue line, this blue plot gets generated, and what it's indicating is that the power of noise is not equally distributed. The higher frequency components have higher power, higher energy, and the lower frequency components have lower power. And this rate is at 3 dB per decade. This slope is 3 dB per decade for beta is equal to -1. And this beta is equal to -1 is nothing but blue noise, and that's the reason why it is shown it in blue plot and blue area under the curve. And what it essentially means is that the higher frequency components of the sound, of the noise, will get amplified or will have higher energy. Now, as we raise this beta to -2, now the power spectral density becomes proportional to the square of the frequency. And so the slope changes, slope becomes higher. Now this, purple color or violet color plot gets generated. It's also known as violet noise or purple noise. And this has a higher slope than in comparison to this blue noise. Blue noise, as I mentioned, has a slope of 3 dB per decade. This, because of squaring action, has a slope of 6 dB per decade. And what it essentially means is that in comparison to blue noise, the violet or purple noise has even higher powers for higher frequencies, and it has lower powers at the lower end of the spectrum. So this is when the beta is negative. Let's talk about what happens when beta is 0, 1, 2. So when beta is 0, essentially f becomes 0, and we come to a constant called constant equal to 1, which is depicted by this green line. Now this is what is the classic definition of white noise, which essentially means that power of the noise is equally distributed across its spectrum. Essentially, the frequency has no bearing on the power, because power is equally distributed at all frequency components. It has no selective preference for any particular frequency, and that's the reason why it's called white. It is a combination of all the frequencies. It's a combination of all the possible colors. And in time domain, it actually is an impulse function, a function which is starting at 0 and going up to infinity. And that's how this white noise gets generated. It's a very important concept. It's also called additive white Gaussian noise. And whenever we study linear filter theory or any kind of linear system, we assume the noise to exhibit this kind of a behavior. It's the simplest form of noise, and it can be easily tackled. Then we come to beta is equal to 1. So now we are talking about a power spectral density, which is inverse of frequency, 1 by f. And this is what is called as pink noise. Now it is exact opposite of the blue noise. It is in the other direction. The slope of this curve is 3 dB per decade. And essentially what it is saying is that the higher power of noise is concentrated at lower frequencies, and the higher frequencies have a much lower power component. Pink noise is again very important. Almost every natural phenomena on this planet exhibits this kind of noise pattern, be it biomedical noises in ECG, EEG, or seismology, or noise in the oceans, or cosmic noise, or semiconductor noise. Every possible thing that you can think of on this planet exhibits this pink noise characteristic. And now when we raise this power of beta to 2, it is basically saying that the power spectral density is now proportional to 1 divided by f raised to the power 2. Essentially, the slope has become steeper. It is 6 dB per decade. And this is what is called Brownian motion, or Brownian noise, or the Brown noise, which is very important from studying from every perspective, including velocity of molecules in a gas, to how electrons behave inside the semiconductors, etc. It's also called as random walk. This type of noise is typically also exhibited in stock market data, in econometric data, and it's again a very important component. A lot of sensors, for example, gyroscopes, accelerometers in inertial navigation systems, they exhibit this kind of noise, including biomedical equipment and biomedical sensors. So what it says is that at lower frequencies, this power in the noise is even more in comparison to pink noise. And a smaller portion of power is concentrated at the higher frequencies. So essentially, it is acting as a low-pass filter, and most of the noise is, is in the lower spectrum, having very high power density, and the higher frequencies are having lesser power; they get attenuated. So now we are going to go ahead and implement. Once we have understood how this whole function is behaving, then we can start generating each of these noises one by one, starting from the white noise. And white noise is nothing, as I said, that it's so we'll essentially define some parameters here first. A sampling rate of 44.1 kilohertz, which is a typical of any sound card that is there in the computer. My laptop has a sound card which goes up to this particular frequency, so I've chosen this. I'll be generating a sound clip or a noise clip of 6 seconds. So 6 seconds multiplied by the sampling rate is the total number of samples that I'll have. I'm choosing my noise mean to be 0 and my noise standard deviation to be 0.2. So as I mentioned earlier, that white noise is nothing, but it is nothing. It is just a normally distributed noise. So I'm using this Python function called random.normal from NumPy library, and defining the mean and standard deviation for this distribution and passing on the number of samples. And then I'm going to generate a time axis here, and I'm going to plot this white noise. Essentially, it's a plot between time axis and the white noise. So let's run this code. And this is how the white noise looks in the time series. So x-axis is time, and the amplitude is y-axis, and 0 mean is what we have specified for our noise. So you can see the noise is split it into 2 parts. Both the parts are looking symmetrical around 0 axis. And 0.1 is the standard deviation, so you can see that the noise is fluctuating around this axis. So I'll stop here, and I'll switch over to PowerPoint to explain the brown noise, and we'll come back to the Python environment.